Hello all of you. Welcome to the 50th lecture on the course on analysis and modeling in chemical engineering. In this week, we have been discussing about separation processes. We discussed the thermodynamics of separation, then we discussed different kinds of cascades. So in this lecture, I will conclude with some examples on cascades and how we can find the degree of freedom of cascades. And in the following week, we are going to discuss how exactly we can set up a computational framework for solving the separation problems. So let us begin with the example that we have left in the previous class. So we have done the derivation for the absorber, but we can do a similar derivation for the stripper, and so let us try to do it. So we are considering a countercurrent cascade of a stripper. So just to remind you, in stripper, the vapor is the MSA, that is my stripping agent, that is basically extracting things from a liquid mixture. So in this case, liquid mixtures enters from the top, and the vapor is going up, and as it moves up, it is taking a component from the liquid, and the liquid is coming down, and as a result, liquid gets depleted in that particular component, right? Now, there is a slight change in the notation of the indices. So earlier, the stages were numbered 1 to n, top to bottom, but now we are doing bottom to top. The reason being that it is dictated by how where the feed is coming from. In this case, the vapor feed is coming from bottom to top, and the feed is my MSA that is kind of going up, right? In other case, the liquid was the MSA. So MSA was entering the first stage from top in the case of absorber, and now the MSA is entering the first stage from the bottom. So we have numbered it differently, so that you will see, you will get the similar kind of language in the final solution. So we have to repeat the derivation, and we are going to get, as we have discussed, something in terms of a stripping factor, that is opposite of 1 over of the absorption factor. So let us try to derive this. Again, we are going to assume that the vapor in the beginning is pure. In the earlier case, the liquid was pure because liquid was the absorbent, the MSA. Now the vapor is the MSA. So in the beginning it is pure. So vapor gets richer in that component as it goes up. So let us try to do a balance for this. So by the logic that we have followed earlier, so I am going to basically do a balance from stage 1 to n minus 1. And what is entering between 1 to n minus 1? So V naught is entering, but V naught is assumed to be 0. What else is entering? So we have a liquid entering from stage n. Whatever is leaving stage n, that enters the n minus 1th stage. So we have Ln that is coming in, and that should be equal to what is going out. What is going out? There is exiting liquid L1 leaving the first stage, now at the bottom, and there is a vapor leaving the n minus 1th stage, L1 plus V n minus 1. Now again we apply the condition of equilibrium. That tells me that my Yn is essentially Kn Xn, and my Yn is vapor mole fraction, that is given as Vn by capital Vn, and that is Kn. Liquid mole fraction is given as the component molar flow rate of liquid by the total molar flow rate Ln, right. So now again I can write my Vn, or I can write now my Ln as Vn divided by Kn Vn by Ln by the rearrangement. In the earlier case, we have expressed the vapor molar flow rate as something like the liquid molar flow rate divided by the absorption factor, but now I am going to do in terms of a stripping factor that relates liquid molar flow rate in terms of the vapor molar flow rate, right? That is the opposite of that, right? So, therefore, we have got stripping factor Sn, that is Kn ln by Kn Vn by Ln, or in general S is equal to Kv by L. Keep in mind earlier we had A is equal to L over Kv. So, S is equal to basically 1 over A. And if I do that, I can write my Ln as Vn by An. And if I plug this in the expression that we have derived, the material balance equation, what we are going to get is essentially my Vn is equal to L1 plus Vn minus 1 into Sn, right. Now, we can now do a material balance from 1 to n minus 2, 1 to n minus 2, and what we are going to get. So, what is coming in? So, V naught is 0, so that is not coming in there, so nothing is coming from there. What leaves the stays n minus 1 in the liquid phase, that essentially comes here, that essentially comes there, and what leaves the vapor phase n minus 2 is what is going out of there, right. So, we therefore have something like what is entering is L n minus 1, that is equal to L1 plus V n minus 2, and now we apply the same logic that we have used earlier. I expressed the Ln in terms of Vn, so I can similarly write Ln minus 1 as Vn minus 1 by Sn minus 1, and if I plug this thing in the expression here, we are going to get Vn minus 1 is equal to L1 plus Vn minus 2 into Sn minus 1. And now, if I plug in the expression of Vn minus 1 from here in the above expression, we are going to get Vn is equal to L1 plus Vn minus 2 Sn minus 1 into Sn, and that is going to give me L1 Sn plus Sn minus 1 Sn plus Vn minus 2 Sn minus 1 Sn. If I continue to do that, you will see eventually this term will go to V0, and V0 is equal to 0, and this term is going to give me the series that is something similar to this. Vn is equal to L1 S1 S2 to Sn, that is going to be last term. So, we have seen here Sn plus Sn minus 1 Sn. If I now substitute for Vn minus 2, we will get something like plus Sn minus 1 and Sn minus 2 Sn and so on. So, we are eventually going to get something like S1 S2 to Sn plus S2, S3 to Sn plus something like Sn minus 1 Sn plus eventually Sn, right? This is what we will have. So, these terms are going to remain, but I will get additional term coming from here, and so the final series is going to look like something like this. And now we can do the overall balance for the component, and that is going to give me something like V naught, which is equal to 0 anyway, plus Ln plus 1 that is coming in is equal to what is leaving Vn plus L1. And now I can define a quantity phi s similar to the recovery fraction we have defined earlier. Now we can define recovery fraction now, but now in terms of the liquid flow rates L1 by Ln plus 1. Again, we want this to be as small as possible because the liquid what is exiting should be having as less amount of the component as possible. It is pretty much similar to whatever we did for the absorber, but in absorber we are looking at the vapor phase because vapor gets depleted. Now we are looking at the liquid phase because the liquid gets depleted. So, this is pretty much going to give me, if you see from here, we are going to get this, but this is now L1 into 1 plus Sn plus Sn minus 1 Sn plus until S1, S2 to Sn, and then the ratio that we get here is my recovery fraction. So, this is going to be 1 over 1 plus Sn plus Sn minus 1 Sn plus S1, S2 to Sn. Very similar to the expression that we had in the case of absorber, but now we have S in place of A in the expression. Okay. So, we can go ahead in the next week to discuss about how we can computationally solve the equations for the separator. But one of the things that we have to do first in order to do that is to define the degree of freedom and to specify every stream, right. So, we have done this kind of analysis for a multi-phase, multi-component system when we discussed the Gibbs phase rule. So, let us try to recap that and try to also see how it will apply for the cascades, right. So, in general, my cascade is going to contain stages like this. Every stage is going to contain streams. So, let us see how many variables we have to specify for each of these streams, right. So, what do we have to specify? For every stream, we can specify the C mole fractions of all the components if you have C components plus the temperature and pressure of the stream. So, total we have C plus 2 variables we have to define for every stream, and the mole fractions are not all kind of independent because they have to satisfy the constraint that the sum over the mole fractions should be equal to 1. So, in principle we have to specify only C plus 1 because the last one can come from the summation of mole fraction equation. And that also comes from the Gibbs phase rule because for a given stream if P is equal to 1, if I plug in P equal to 1 in my Gibbs phase rule, so we have as you see here C minus 1 plus 2 equal to C plus 1. So, for every stream we have to specify C plus 1 variables. Now, for the extensive, so this is true for the intensive variable. Let us look at the extensive variables. So, for extensive variable for every stream we definitely need to specify total flow rates, because once we specify that we can find component flow rate by multiplying the total flow rate by the mole fraction. the mole fraction already has been specified. So we only need the total flow rate in this case. So therefore, in total, we have C plus 1 intensive variable and 1 extra extensive variable. So we have C plus 2 intensive and extensive variable, right. What we are going to do is, rather than saying that we have to specify C plus 2 variables, we will count all the C plus 3 variables and say that one summation of mole fraction equation applies. So we will basically specify all the C plus 3 variables in our numerical scheme, but then we enforce the condition as this equation. It just becomes neater to write, because in the end we are going to do number of variables minus the number of equation. So one possibility is that we don't consider the last mole fraction as a variable. In that case, we don't have to use summation of mole fraction equation. Let us say for a binary system, we have two mole fraction x1 and x2. I can say I have a single variable here x1 and x2 comes from 1 minus x1. So I don't define this equation. I simply say I have a single variable x1, right. That is one possibility. In that case, I am counting only one variable and I am not counting this equation. So therefore, this will give me a DOF is equal to 1 for that system, right. Or I can say I have two variables, but they satisfy this equation, and again we have degree of freedom is equal to 1. So as long as we are adding equation in the equation side, we can essentially add a variable in the variable side, because in the end what we care about is the number of variables minus the number of equation. So as long as the degree of freedom is unchanged, that is completely fine, right. So just for kind of clarity, we are going to specify all the variables in our listing of variables. Which one will I be given and which one we have to choose, that's a separate story. These are the variables which I am listing as the variables in the problem. Of course, whatever the degree of freedom, those number of variables we have to specify, that is a separate thing. Here I am simply listing all the mole fraction as the variable. So in total we are listing C plus 3 variable in every stream and one equation that correspond to the summation of mole fraction. So now if I look at an equilibrium stage, they have two input streams, provided that it's a binary two phase system. So it has two liquid streams, two vapor streams, or it can be two phases containing L1 and L2, doesn't matter. In total it has four streams, two inputs and two outputs, and for each of that we have to specify C plus 3 variables. And then an equilibrium stage may have a heat transfer or heat exchange. So I add an extra variable Q, and that is all I have to add, because the molar flow rates and all that it's already taken care of, and we are not considering chemical reactions happening inside the equilibrium stage, right. So in total we have 4 into C plus 3 variables from the streams and one variable, that is the heat added. So total we have 4C plus 13 variables. And what equations do we have? So we have a pressure equality, we have a that is something like, for the two phases, P1 equal to P2, we have a temperature equality, T1 equal to T2, and then we have phase equilibrium relation that comes from essentially mu I in phase 1 is equal to mu I in phase 2, but now we have a simplified way of writing it in terms of the mole fraction, right. So and then we have, in total we can write C component material balances, or we can write 1 total material balance and C minus 1 component material balances, right. So if we do C component balances, then we cannot do total material balance, because adding up all the component balances gives me the total balance, right. But total balance sometimes is more intuitive to write and also helpful. So therefore we write 1 total material balance and only C minus 1 component material balances. Keep in mind that we have to keep our equations independent, right. So if we would have chosen to write C component material balances, then total material balance is no longer independent. So therefore, we are choosing only C minus 1 component material balances, because the other material balance is the total one. And then we have one energy balance, and then we have for every stream, as we said earlier, we are considering the summation of mole fraction as an extra equation, because we have added an extra variable for every stream, right. So we have 4 summation of mole fraction equations. Total number of equations is 2C plus 7, and therefore the degree of freedom we can now calculate. It's 4C plus 13 minus 2C plus 7, that is equal to 2C plus 6. That is the number of degree of freedom for every stage in the cascade. So now, what can be possible choices for the 2C plus 6 variables, right? So one possibility is that we can specify the component mole fraction, the C minus 1 of them, because the last one will come by the summation equation for every phase. So we have 2 phases. So we can specify C minus 1 component mole fraction for both phases. We can specify 2 input flow rates coming in, and we can specify basically 2 stage pressures, right? One for the vapor that is going out, and one for the liquid that is going out. We will see they are in equilibrium, right? And then finally, we have 4 temperatures and pressure of this, right. So both temperature and pressure for this liquid and vapor, but for these two I am only specifying the stage pressure, because the other thing may come from the equilibrium condition. Keep in mind that L in and V in is not in equilibrium, but L out and V out are both leaving the same stage, so they are in equilibrium. So temperature will be evaluated from the equilibrium condition. So whatever, once we have identified the pressure equilibrium, we can get the corresponding temperature. So total variables therefore is 2C plus 6 that we can add up and get there. And now we can go ahead and apply this idea to a cascade of these stages, right. So as we have noted, we had 4C plus 13 variables for every stage identified earlier. But now there are some redundant variables that appear twice, right. So let us say, for example, Vn minus 1, Vn minus 1 is leaving stage n minus 1 and entering stage n, right. So we should either consider it for the stage n minus 1, or we consider it for the stage n. That is true for all the intermediate variables here. It is not true for the 4 output variables, right. So for all the intermediate variables, it is basically coming from somewhere and going somewhere. So we have to count it only once, not twice, right. So therefore, in our variable counting, we should avoid the double counting of the interconnecting stream. And how many we have? We have 2 into n minus 1, 1 for each phase, right, and n minus 1 variables, because we are going from stage 1 to n minus 1. There are going to be n minus 1 interconnecting variables, right. And finally, we have one extra variable, that is the number of stages that we are having, right. So we have for every stage, we have 4C plus 13 variables, as we have counted earlier, 4C plus 13 variables for every stage. But then we subtract the redundant streams. So we have 2 into n minus 1 redundant streams, and for every stream we have C plus 3 variables. So we are multiplying by C plus 3, and one extra variable for the number of stages, and therefore we can count total number of variables. And then we can also count the number of equations. So actually, we already have the number of equations figured earlier. So we have seen we have 2C plus 7 equations for an equilibrium stage, but again we have to remove redundant equations which are appearing twice, which are for all the interconnecting streams that we have in there, right. So you can see we have n into 2C plus 7, that is the number of variable, but I subtract the redundant variable, which is 2 into n minus 1. So for every redundant variable, we have a summation of mole fraction equation, which is basically getting double counted if I do not subtract it. So therefore, I simply subtract 2 into n minus 1 from here, and I get the number of variables, and therefore now we can compute the degree of freedom as something like this. And then the question is that which of the variables I should choose. This is one possible choice of variables. We can specify the stream variables for the two vapor streams, right? And keep in mind that I am not keeping a C plus 3 here, I am doing a C plus 2. So I am only specifying one less mole fraction, because the last one can come from the mole fraction. So for the inlet and outlet, I am not considering the summation of mole fraction equation in my scheme of things. If I want, I can list them, that summation equation for these two as well, and in that case I will put a C plus 3 here. So keep in mind that whenever I add an extra variable on this side, that is kind of redundant, because I am adding an extra variable that can come by the summation of mole fraction equation, I have to add the summation of mole fraction equation on the equation side. So for everything intermediate, in fact we are doing that. We write the summation of mole fraction equation, but we also consider all the component molar flow rate. But for V in and V out, I am choosing not to do that, and I am not writing the summation equation separately for these. So therefore, I am considering only C plus 2 variables, right. Now we can also specify the heat added for every stage, and I can also specify the stage pressures, and I can also specify the number of stages that we have, and we can get the total here, right. So keep in mind that the choice of the specified variables which I have made is not unique, but it is made with keeping in mind that choice basically makes my solution consistent and easier when we look at the final set of equations. But in general, you can have other possible choices of the specified variables as well, right. So what has to be kept in mind, that whatever is the degree of freedom, those number of variables we have to specify, but the particular choice which I am showing here, that is not something which is very unique. Okay. So we can go ahead and do other kind of examples, but there is one thing which I want to mention here, that is, in so far we have always assumed the condition of equilibrium, right. But in general, it is not kind of true always, right. There can be situations where the equilibrium is not attained, and in fact there is going to be more of that situation, right. So I will not solve this particular problem, but just giving you a hint of cases where an equilibrium condition is very hard to maintain is the following. So let us say in the raffinate phase we have a chemical reaction going on, and we have a membrane separating the raffinate and the permeate. So one of the component is not absorbing as such, but it is basically passing this membrane and going on the other side. But there is a chemical equilibrium taking place. Raffinate contains A and M can enter the permeate phase, and the permeate also contains some solvent, let us say it is coming in. So now since there is a chemical reaction that is taking place, it is going to have a differing rate along the length that we are seeing here, right. So when we try to compute the net flux that is going from the raffinate to the permeate, that flux is going to be strongly dependent on this chemical reaction. So in fact, we have to go back to the basics and write the general unsteady state mole balance for the species A and M here, and in the raffinate phase and in the permeate phase, right. So let us try to set up that problem and see like what exactly it may look like. I will not completely solve it, but just to set up the problem. So in this case, I will consider a differential element, and then I will write the mole balance of A in the raffinate phase, let us say. So how can we write the mole balance? Let us say this is x and this is x plus delta x. So the mole balance will have Fa coming in minus Fa leaving out, right? And then A gets consumed, so we have minus Ra into the area. So let us say this area of cross section is A1 here. So A1 delta x, and that is equal to something like V dCA by dt in an unsteady state, right? And then I can also write it for basically M in the raffinate phase. So A was not going out from raffinate to permeate, but now for this case we will have Fm coming in, Fm leaving x plus delta x, and then we have production of M in the reaction. But now there is also a flux going from the raffinate phase to the permeate phase, and that also we have to account for. Multiplied by whatever area that we are having there, right? So that also has to be done for, and similarly we have to write the mole balance for the permeate phase for the component M. A is anyway not going there, right? So by the way, this is unsteady state. So we should have, sorry, it's not V, it should be A1 delta x. It is delta V, so A1 delta x dc m by dt, where A1 is the cross section area in the raffinate phase, right? So whatever condition that we have assumed of the steady state or of equilibrium, those we were still able to do because we assumed in all the cascades that we have discussed that there is no chemical reaction taking place. Once there is a chemical reaction taking place, then the situation gets more complicated. In addition, like in this particular case, we have a membrane separating the two components. So therefore, we have to also account for the actual mass transfer, the flux considerations, which will basically deviate the system from the equilibrium situation, right? So in reality, we should always basically go for what is known as the rate based models or non-equilibrium kind of models, because non-equilibrium is more closer to reality than the equilibrium that we assume. But as you see here, like even for this simple example, that the equations gets more complicated. Instead of algebraic equations, we start to have differential equation, and situation gets much more complicated once we look at non-equilibrium effect, right? So later in the course, we will discuss how exactly we have a rate-based treatment that accounts for the mass transfer effect properly in separation processes. But in the next week, we will start with discussing first the equilibrium-based methods, how exactly the equations that we developed for the cascades or a general kind of equilibrium states can be solved on a computer. So with that, I stop here. Thank you so much.